seems to me that a lot of owners expect their cars to have the roadability and handling characteristics of a sports car, the durability and load-carrying capacity of a truck, and still produce a ride as soft as floating on a cloud. As a matter of fact, I've known more than one technician who got into a peck of trouble because he juggled front-end alignment, steering geometry, wheels, tires, springs, and shocks, trying to satisfy a customer who expected the impossible or was overloading his car. I've run into quite a few cases of technicians blaming front-end alignment when the trouble was rear springs, incorrect tire pressure, or overloaded tires. I think it's high time we reviewed steering, suspension, and handling. I think we can all learn a thing or two by listening to Ed Wallace explain some of the fine points of the things that affect car stability and handling to young Ray Dykes. Are you all set for a lesson in roadability, Ray?
Sure am, Tech.
How about you, Ed? Are you ready to explain some of the most important things that affect handling?
Well, I guess I'm as ready as I'll ever be. Of course, I'll be counting on you for a lot of help, Tech.
You ought to know you can depend on me to put in my 2 cents worth, whether you ask for it or not. But this is your show, Ed, so put it on the road.
Okay, Tech, here goes. I want to repeat something you mentioned earlier, Tech. I've seen some pretty good technicians waste a lot of time working on the wrong end of the car. There are several reasons why it's easy to make this mistake. Failure to identify the exact nature of the customer's complaint is probably the most common reason for getting off on the wrong track.
Believe me, you can't trust an owner's description of a handling problem to mean what you think it does. I've heard them complain of handling, roadability, wander, drift, roll, sway, yaw, and wow. I remember one gal who described her handling problem as squashy. She had a low rear tire. Rule number 1 is road test the car with the owner. Have him or maybe her demonstrate the condition to be fixed.
Well, what if you can't get the owner to take time to ride the car with you?
In that case, find out as much as you can about the complaint by asking questions. What kind of road? What speeds? How much load in the car? Does wind cause the problem? Straightaway or curves? When you get all the information you can from the owner, road test the car to see if you can duplicate the condition the owner is complaining about for yourself.
If you can't find anything wrong with the way the car handles, you better insist on a ride with the owner. The knack of finding and correcting the cause of a handling complaint is partly a matter of experience and partly a matter of knowledge.
What kind of advice do you have for a guy like me who doesn't have much experience?
Here's a very general thumb rule, Ray. If you have to constantly correct or move the steering wheel to keep the car going straight ahead on a smooth, flat road, no overload and no crosswind, suspect steering, front end, and front tires. Of course, if the problem is returnability, the trouble is steering gear adjustment or alignment, steering linkage, or maybe front end alignment. But on the other hand, if the problem is primarily sway on turns or fishtailing, suspect the tires, tire pressure, springs, or too much load. The trouble is most apt to be at the rear end.
There's an exception to that rule. At highway speeds, a car with poor returnability may feel like the rear end is fishtailing. But instead of just talking about the way a car feels, why don't you explain to Ray the things at the front and rear of the car that contribute to stability when they're right, or cause handling problems when they're not?
That's a good idea, Tech. I think I'll start with front-end geometry. As you know, a wheel has positive camber when the top of the wheel leans outward away from the car. Actually, zero camber would be best for driving on straight, smooth, level roads. Steering a car around curves or on crowned roads is something else again. Let's consider what happens when a car rounds a curve at highway speeds. Centrifugal force causes quite a weight shift toward the outside wheel. The car body tends to move downward, closer to the outside wheel. This relative movement between the wheel and body is called jounce. It's the same as having the wheel move upward toward the body when it hits a bump. Because of the control arm geometry engineered into our suspension systems, the top of the wheel moves inward, resulting in negative camber at the outside wheel. In other words, the wheel has negative camber when in jounce.
Is that negative camber at the outside wheel important?
It sure is, Ray. That negative camber at the outside wheel helps the tire tread bite in. It braces the tire tread and reduces slippage toward the outside of the turn. Negative camber is important on crowned roads, too. Tell Ray why, Ed.
On crowned roads, there's more weight on the low or outside wheel. It goes into jounce, changes to negative camber, and leans uphill. Because it leans uphill, it tries to roll uphill. This helps offset the tendency of the car to drift downhill toward the side of the road.
What happens at the inside wheel?
On a curve or crowned road, the car body moves upward away from the inside wheel. This puts the inside wheel in rebound. Camber changes a little, but not as much as it does in jounce. In other words, our front suspension control arms are designed so that there is a camber change in both jounce and rebound.
The feature of negative camber in jounce and a lesser negative change in rebound contributes to the excellent handling and cornering characteristics of our cars.
What happens if the camber isn't right?
Incorrect camber usually affects tire wear more than handling. Of course, if camber is quite a bit out of specs, you may get hard steering and wander. A big difference between right and left wheel camber can aggravate low-speed shimmy.
That sums up camber. Now let's tackle caster. A furniture caster is the best illustration of caster effect I know of. When you move a piece of furniture, the caster wheel trails behind the caster's pivot point. In other words, the pivot leads the wheel and pulls it along, so it follows the direction you're pushing. If you drew a center line through the pivot, it would intersect the floor line in front of the caster wheel. This is an illustration of positive caster. The principle is the same for a car's front wheels. The center line of the pivot, called the steering axis, is tilted so that it intersects the road at a point that is in front of the wheel contact with the road. This is positive caster. If the steering axis is tilted the other way, the caster is negative. On today's cars, caster angles are very small. Positive caster does contribute slightly to directional stability, and it also helps the front wheels return to the straight-ahead position.
Positive caster is specified on cars equipped with power steering because it increases returnability and contributes slightly to directional stability. Positive caster does increase steering effort somewhat, but that's no problem where power is doing the work. On cars with manual steering, a small amount of negative caster is used because it reduces steering effort. This doesn't affect stability because modern cars get most of their directional stability from steering axis inclination. We'll get to that as soon as Ed finishes with caster.
Too much positive caster will cause hard steering. Of course, this would be most noticeable on a manual steering job.
Well, how would it affect a power steering job?
A power steering equipped car with too much positive caster may develop an objectionable low-speed shimmy and wander at higher speeds. With too much positive caster, you'll feel more road shock through the steering wheel. Unequal caster or negative caster at one wheel and positive caster at the other represents the worst possible condition with respect to handling. The car will drift toward the side with less caster and may pull sharply to that side when the brakes are applied.
Well, it sounds to me like incorrect caster settings can cause handling problems, and caster ought to be set as close to specifications as possible. But say, weren't you going to explain steering axis inclination to me?
Coming up, Ray. The steering knuckle is made so that the angle between the steering axis and the steering spindle is more than 90 degrees. In other words, the steering axis isn't vertical. It's slanted inward at the top.
And that angle increases directional stability?
It sure does, Ray. Because of steering axis inclination, car weight helps keep the front wheel spindles pointed straight out and the wheels pointed straight down the road.
Well, I don't see why. Can you explain it another way?
Inclining the steering axis is something like hanging a swinging door or gate, so the hinges are angled, not lined up vertically. The gate will always swing closed. The forces and angles aren't exactly the same, but the principle is. Steering axis inclination is designed into the steering knuckle. You can assume it's okay if you can adjust camber to specifications. About the only time you measure steering axis inclination is to detect bent or damaged parts. You'll find a lot more detailed information about caster, camber, and steering axis inclination in the reference book, so be sure and read it. Right now, someone better turn the record over.
I never could understand why front wheels should be towed in. It would seem to me that they should point straight ahead without any toe in or toe out. Why have toe in?
The main reason why toe in is specified is to make sure there isn't any toe out. Toe out causes wander as well as excessive tire wear.
Why not adjust the front wheels to zero toe?
To obtain zero running toe, there has to be a small amount of toe in when the car is standing still. Let me explain why. Under operating conditions, the rolling resistance of the tires and brake applications are forces which try to compress the tie rods and steering linkage. This tends to let the front wheels toe out. That's why a small amount of toe in is specified when the car is at rest.
Be sure and inspect the tie rod ends, steering linkage, and wheel bearings for looseness. It doesn't take much looseness in the steering linkage to let the wheels toe out under running conditions. Of course, any binding in the steering linkage or steering gear is just about as bad as looseness when it comes to handling and returnability. Care to comment on that, Ed?
You bet, Tech. Any interference or misalignment in the steering system will affect handling and reduce returnability. Good alignment and freedom from binding is particularly important on power steering models having the intermediate steering shaft and two couplings. For example, too great an angle between the lower coupling and the intermediate shaft will increase friction and affect both steering and returnability. The angle should be as small as possible. Another thing, the intermediate shaft must be correctly located or centered in the lower coupling. If the shaft is too deep in the coupling, it may bottom when the steering wheel is turned and cause a lumpy feeling.
How do you check the coupling and shaft alignment?
You'll find detailed information on steering column alignment in the reference book for session 65-5, so we won't take time to go into the nuts and bolts details. Besides, we still have a lot of ground to cover on other things that affect handling. You'll also find more information on steering gear alignment, steering gear adjustment, and steering linkage in the reference book for this session. Right now, hear what Ed has to say about slip angles.
Let's get a couple of facts about slip angles straight right at the outset. Slip angle does not mean tire slide. Slip angles have a very important effect on car handling, particularly on cornering ability. To understand slip angle, you have to visualize what happens to a tire when a car is cornering. For example, this is what a cornering right front tire looks like on a curve to the left. If you could look through the same tire from above, you'd see that the tire contact or patch area is twisted so that it is pointed in the direction the car is headed. At the same time, the car wheel is turned at a greater angle. So you can see, Ray, the tire is not actually sliding, but we call this condition slip angle. For all practical purposes, the slip angle is the angle between the direction the car is headed and the direction the road wheel is pointing.
Do you get this slip angle effect at the rear of the car, too?
Yes, you do, Ray. Ed will explain understeer and oversteer.
Let's suppose that you could see the slip angles of a car going around a curve, and the front slip angles are greater than the rear slip angles. Because of the smaller slip angles at the rear wheels tend to track inside of the front wheels. In other words, they tend to follow the turn closer than the front wheels. This understeer is a desirable safety feature.
You bet it is. Understeer helps keep the rear end of the car from trying to catch up and pass the front end of the car when you take a turn at high speed. But there's more to rear end steer than that. Ed will explain how we design understeer into our rear suspension.
When a rear wheel moves upward into the jounce position, it also moves forward. That's because it is moving in an arc. The center for this arc is at the front spring hanger. The forward movement of the rear wheel in jounce causes the entire rear axle to turn slightly and steer the rear end of the car. Let's see which way this rear end steer works on turns. The outside wheel has the extra weight on it when the car is in a turn. Therefore, it is the outside wheel that moves into jounce and moves forward. This means the rear axle steers the rear of the car toward the inside of the turn.
Now I get it. The rear end steering into the turn is understeer. This reduces the tendency of the rear end to break away and try to pass the front end, right?
Exactly, Ray. And now that you understand understeer and slip angles, I think we're ready for a lesson on tires, wheels, and springs.
Correct front-end alignment and freedom from binding or looseness in the steering system is very important. However, low tire pressure, overloads, tire size or type, and rear springs cause far more problems than you might suspect. I'll give you some good examples of what I mean. When a tire is underinflated or overloaded, the lateral deflection or side-to-side movement tends to increase. Since the slip angle also increases, side sway and cornering stability is adversely affected. When a car is overloaded, most of the extra load is concentrated on the rear end. It's human nature to put the heaviest things in last and leave them near the back of the car. An overhanging load puts extra weight on the rear and reduces traction at the front. The simplest and one of the most effective ways to increase load-carrying capacity and stability is to increase rear tire pressure.
You'll find the latest up-to-the-minute tire pressure recommendations in the reference book. Be sure and use this information. And speaking of tires, don't ever forget that the only contact the car has with the road is through the relatively small patch areas of the four tires. All car directional as well as starting and stopping control is concentrated at these four tire contact areas.
That's a most important point, Tech. And since lateral stability is related principally to tires, wheels, and vehicle load, it's easy to understand why oversized heavy service tires mounted on correct width rims are recommended in many instances. This is particularly important on heavily loaded vehicles such as station wagons. Here are some things to remember about tires. Match tire and wheel. Don't put an oversized tire on a wheel with an undersized rim. If the rim is too narrow for the tire, the sidewalls will bulge excessively and you won't gain anything in load-carrying capacity or stability. On a stability complaint, be sure and check tire size and type. I found that snow tires allow more rear-end sway. It's even worse if the owner uses undersized snow tires, maybe from a previous car. Putting highly cambered rear springs, booster springs, or any other equipment to make the rear end ride high so it'll carry a bigger overload with less bottoming is asking for stability problems.
Well, why is that?
Our rear springs are designed to have little or no camber under light loads and a small amount of reverse camber under heavier loads. In other words, they are supposed to be relatively flat, not highly curved or cambered. This gives better lateral stability than a highly cambered spring for two reasons. A flat leaf spring resists side sway better than a highly cambered spring for the same reason that you can't swing a tight rope from side to side, but it's easy to swing a limp rope which is arced or cambered. Anything you do to the rear end of the car to make it ride high will increase the camber of the rear springs. This reduces lateral stability. Too much rear spring camber has other undesirable effects. Raising the rear end of the car upsets the desirable understeer geometry designed into the rear suspension.
If you change rear spring camber too much, you might even get into oversteer, and you don't want that.
How about factory-installed heavy-duty rear springs? Don't they have a lot more camber than standard production springs?
No, Ray. They're stiffer for extra load-carrying capacity, but they are virtually flat for good stability.
Here's something to remember about optional equipment like heavy-duty rear springs, heavy-duty torsion bars, heavy-duty shock absorbers, and sway bars. The complete factory-installed heavy-duty suspension package is a balanced design. If an owner is going to haul heavier than normal loads, he should order a car with heavy-duty suspension, wheels with wider rims, and larger tires. That's a lot better and cheaper than trying to rebuild a standard production car in the service department. Of course, there are some things you can do to improve handling in a car that wasn't ordered right. There are also a lot of things you shouldn't experiment with, like booster springs and big tires on narrow rims. You'll find more about these things in the reference book. As a matter of fact, there's a lot of detailed information in the reference book that we didn't have time to cover. Besides, you probably wouldn't remember things like tire pressures, tire sizes, rim widths, and heavy-duty option information if we had put it in the film. With more families taking to the highways loaded down with vacation gear, car handling is increasingly important to your customers. Take time to bone up on the subject of roadability and be prepared to answer their questions and handle their problems.